Good day and welcome to your WTW 258 course for Theme 2. So Theme 2 is filled with loads of integrals and also with a lot of visualization skills that is needed. The way to study for Theme 2 is to do a lot of practice problems, but to try and understand the work instead of just reciting something that you've seen somewhere before. So we'll be diving straight into Theme 2.1. So in Theme 2.1, you will be learning about double integrals and how to use double integrals and what they mean. So before we actually jump into double integrals and what we use them for, I want to give you a basic idea of what the integration for a double integral would look like. And how to do this would be with Riemann sums. So Riemann sums are used to approximate volume. So as you can see here, the Riemann sum, this is just the formula for the Riemann sum, is equal to, well, it approximates the double integral. So this double integral will give you volume. So what a Riemann sum does is when you want to calculate the volume in between a surface area and an area on a plane, it breaks up the area on the plane into small rectangles, sometimes small squares, and then it takes a height function, which is this function, and then it takes the area of each rectangle or square and it multiplies it by the height function. And then it does that for every square or rectangle. And then, so that's how you approximate the volume. Just a few things. The m that you will find is how many divisions you will have in your y interval, and the n is how many divisions you will have in your x interval. And the fxy is just the height function that you use to approximate the volume. The del A is the area of the small rectangle, and note, since the whole area will be divided into m and n, you will have rectangles that are all the same, with all the same area. So the purpose of using the Riemann sum is just to approximate a volume underneath a surface. So then it leads us to example 1. Okay. So in example 1, they give us a region. Note how we write a region. So this is a region where you have x and y, and where x is between 0 and 2, and y is between 1 and 4. Okay, and then they give us m is equal to n is equal to 2, so both your y and your x intervals will be divided by 2, and we have our height function, which is rxy. So before we do anything, we discuss the steps that we take. So we can start with dividing our intervals into 2. So our x interval is from 0 to 2. So the length of the interval is 2. So our x would be 0, 1, and 2, because we divide the length by 2, which will give us 1, and then we say it's 0 plus 1, which will give us 1, and then it's 1 plus 1. And we denote these numbers by x0, x1, and x2. We then do the same with y. So the y interval, as we see here, is equal to 3. The interval length is equal to 3. When we divide the interval length by 2, we get 1.5. So it'll be 1 plus 1.5, which is 2.5, and then 2.5 plus 1.5, which will give you 4 again. To interpret it visually, we have this diagram where we can see how our region is divided into the rectangles. So you will end up with 4 rectangles. Okay. And now we discuss how do we use this and put it into our Riemann sum function. So to get our area for the Riemann sum functions, we need to look at the area of the small rectangle. So if you want to, you can, with each question you do, you can draw this for yourself. But what you can also do is you can just say 1 minus 0 times 2.5 minus 1. And this will give us an area of 1.5 later on. Okay. So in this question, we usually just use x1 and x2 and y1 and y2. So we say 1 and 2.5, and then we put it into our function here, and then we multiply it by our area. And then we use 1 and 4, and we put it into our function, and we do the same. And then we do the same for the 2, 2.5, and 2 and 4. And we put it into our function, and we will later get values. So then we get the values in your function, which is 7.5, 12, 15, and 24. And you multiply it by the area that we got from our equation, and that will give you an approximation for the volume of 87.75. So that is how a Riemann sum works. But we also have the midpoint rule, which is just a little bit different than the Riemann sums. So where it differs is for the x and the y that you put into your function and that you use for your delta A to get your area, you get a midpoint between your divisions. So I'm going to explain this by using the same example that we just used for the Riemann sums. So we have the same region, and the same x and y, and the same division as well. So our x and y values are exactly the same as previously. The difference is now, so we get a value in between 0 and 1, and 1 and 2, and 1 and 2.5, and 4. So our first value will be a half. So you say 1 minus 0 divided by 2. Usually you can say plus 0, but I left it out since it is 0, and that would be a half. And then the second x value would be 2 minus 1 divided by 2 plus 1, because you have to take into account the numbers before 1. If this was a half, then you would have had to say just plus 1. So then you just have to take into account this number as well. And then we do the same for the y values. So we say 2.5 minus 1 divided by 2. And then we take into account the 1 plus 1 is 7 over 4. And then we do the same for the second y value, which is 4 minus 2.5 over 2 plus 2.5 is 13 over 4. So now we have the values that are in the middle of these. Okay. Now I'll show you how we use them. So the first thing we can check is the area. So how we calculate our area would be, we would take the difference between these middle x's that we calculated, which is 3 over 2 minus a half, and then we would multiply that by the difference between the y's that we calculated, which is 13 over 4 minus 3 over 4, which is 2.5. If we had to visually draw it, this is what we did. So these are the rectangles that we had previously, but in each rectangle we now found a middle point in each one of them. And now we approximate it even further by taking the area of this rectangle instead of each one of them. And now when we want to plug them back into our function, we do the same as we did previously, but we use the middle points. So we will have a half and 7 over 4, and a half and 13 over 4, 3 over 2 and 7 over 4, and 3 over 2 and 13 over 4. So it's almost like the Riemann sums, but it uses the middle points. And then you just put these values inside your function again, and you get these results. And then you just add them up, and you will get a new approximation for your volume, which is 75. Now, if we actually integrate this, it gives you about 45. So the middle point rule gives you a better approximation of the actual volume below the surface than the Riemann sum does. Okay, and now we just move on to another important thing that is asked in question papers is the average value of a function. What we mean with the average value of a function is basically the average height of the surface area. Previously, we had a different height for every rectangle. And sometimes it's useful to have an average value of the height, especially if your surface isn't extremely curvy. So the equation we use for the average height is it's 1 over the area of the region. Now the area of the region is the area of that whole area that we had before. It's not just the area of the small little rectangles, it's the area of all of them added together. And then 1 over that area times the integral of your surface area. So to put this more simply, this is your height, this is the area, and this is your volume. And then we see an equation that we've met before probably with any other mathematical question where you had to get the height of a function. The height of something is always the volume over the area, and that just looks the same as 1 over area times the volume.